Hopefully, yes. Um, so we started talking about model selection, and this is sort of an interesting, I would say, important problem. And so, if you recall, the so anyone remembers what model selection was about? Just remind me what model selection is. See if you guys are on board. What is the problem of model selection? So we have a bunch of models for data. We want to pick one. So let's say, what is a good model? How do you pick a model? You want to, yeah. 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 Yeah, that's a very good point. So I had something here about what is a good model, but this is not obvious. So one thing that Theas pointed out is, let's say machine learning or um, AI, if you want, or that sort of line of thought, you usually care about predicting future values or future data. And so a good model is a good model which has the best predictive power, sometimes referred to as good generalization error. This is the standard in let's say machine learning, CS literature, and AI, if you want to call it, deep learning, things like this. That's the gold standard. Statisticians sort of traditionally view things a little bit different. So, so there's like at some point this quarter we have a lot of time. We have two lectures, so we can explore this a little bit more in details. But like the cultural statistic is a little bit different. So you don't start with predictive um, accuracy. So a good model is often thought to be a model that fits the data well and sort of is simple, or it's measured by the number of parameters. And the idea is you have a model, a true model. That's what usually statisticians assume. There is a true model, and it's hopefully one of these. That's the assumption, and you want to pick the right one. You want to pick the actual thing that's generating the data. This might be looks very naive, but that's how people think. So you think that if I enlarge this class of models, this is big enough, then it includes my sort of data generating process. There is a true model that's generating data, and my goal is actually to find that model. Why do I care about that? Because then I can understand what is going on in data. So I can sort of do like science, let's say. You want to see which gene sort of influences this disease. There could be multiple, like there could be many of these that predict well, but they could vary, like they could provide different explanations. So you could have two very different models that have a very similar predictive power. And the traditional idea, classical idea, and the statistic was you want the actual model, which is like something to debate. But let's keep with this. For now, we're gonna assume that there is actually a true model, and it's one of these. And one of the things that you might ask is, oh, maybe this is the true model might not be simple. It's a fair point. But this is another assumption that we're going to make. So there is a true model, and the true model is simple. Okay. And then you're going to find that model. The reason why you would want to assume that the model is simple is because you can't find the complicated model. unless you have huge data sets. So we get back to this. So I'm happy to talk about these things because they're not obvious. But let's get to some concrete model selection procedures, and then we'll come back and talk about interesting stuff. So one of the things that you can do is that you can assume that, for example, in the context of linear regression, there is a linear regression model, okay? And there are a bunch of covariates, like x1 up to xq. These are all the covariates in like possible. We've included everything that's possible. And then you only, okay, so low MSE. And that's related to what is a good model. So we'll come back to this if, so MSE is usually, it depends what you call MSE. We'll get to the MSE in a few slides. Yeah, so we assume that there is a linear relation, and we want to pick the model among these linear regression models that's the simplest and it still fits the data best. That's sort of the goal. One idea is that that would provide the best explanation. So if you can explain a complex process by 1,000 variables versus 2 variables, the one with 2 variables gives you a lot more insight. And if it's possible to go for that, the simpler explanation is preferred for the reasons of interpretability. So you can assume that the actual model is sort of simple, and then try to find the simplest that fits your data. But so this is debatable in any case. What you should understand is that if you have few covariates, there are 2 to the q possible linear regression models between y and these variables, depending on which ones I include. So everyone sort of understands this 2 to the q. You can just list them, and it's just a combinatorial idea. The number of subsets of all the subsets of a set, the 3 elements, all the subsets amount to 2 to the 3, if you have 3 elements. The empty set would be the model that doesn't include any covariates, and the entire set is the one that includes everything. And so you get this 8 different models, and then I sort of can group them in terms of their complexity. So this is the least complex model. Basically, there's no modeling. There is a little bit of modeling, beta 0, but usually this is the smallest, like the null, the default null. There's no relation between y and x. And these are the simplest, let's say, models of relation between x and y, and then this is the most complex. And so the first criteria that we have for a good model is that it fits the data well, and that we can easily measure by, let's say, in linear regression by R-squared. Yes. Yeah, no, so yeah, part of the thing is that the true model is one of these, okay? If there is interactions that you can, for example, there's like x1, x2, x2, x3, x1, x3, you can all add them as covariates. So I can think of, if I want to model interactions, and that's not the only possible way to have interactions, but I could, for example, add these 2 things. X1, x3, x2, x3. Okay, and treat them as new covariates, and then think of a model. But if I do that, usually it's better to include more. No one knows what else is better to include here if I want to include these. So if you do this, just the model would have some trouble like hitting things. So by experience, you realize it's better to include also all the possible quadratic. So these are all the possible quadratic terms. So if you let this and linear model that includes all these covariates would allow you to fit a general degree 2 polynomial. If you don't include these things, then some weird things happen from practice. Try to do this in practice, and you try to simulate x1 squared by x1, x2, and the other ones. If there is some sort of a simple, maybe the relation is something like beta 0 plus beta 1, x1 plus beta 2, x2, x1, 2, but you don't have x1, 2, then the other variables sort of try to make up for this, and things blow up, and interesting things happen. So some counterintuitive things happen. So it's good to include everything of the second order. And if you go to the third order, every possible monomial of the third order, that would allow you to model a general polynomial of degree 2 or a general polynomial of degree 3. So if you think about this, like there are 6. So, and you can see like the model sort of the dimension. So you treat all these as new covariates. Okay, so you have like now 6 more covariates. And so I get, let's say, 2 to the 6 possible models. And 2 to the 6, what is 2? Sorry, no, 2 to the 9. What is 2 to the 9? Any computer scientists? Powers of 2 by heart. 2 to the 9? Not computer scientists. Like 5. Well, 2 to the 10 is like 1,024. Too many models, okay? You can see it like easily blows up. You go from 8 to like 500. Okay, so any other questions? That was a good question. So the assumption is that you're picking from these. One of these is the true model, which is often very unrealistic. Fine, like a first approximation. Another chat here. Great. Okay, you have one computer scientist. So, okay, so we can like easily compare them in terms of the R squared. And last time I mentioned, hopefully you understand that there is a relation between these models. Not all of them, but the R squared of nested models are comparable. So M23 is a super model, let's say, of M2 and M3. So these are nested within this. So the R squared of this is going to be bigger than either one of them. But the models that are in the same, let's say, level, M1, M2, and M3, we can't directly compare the R squared here. But there is some sort of relation like this, so that the R squared of M13 is going to be definitely bigger than every one of the other guys. And you've seen this before, that this tells you that R squared alone is not the best, or it's like not necessarily a good measure of, or a good criterion for model selection. Because if that's your criterion, you're going to take the biggest model always. That's not what we want to happen. So the model selection criteria try to balance out this measure of fit, which is reflected in R squared or some other quantity related to R squared, and the complexity of the model. The first one is this adjusted R squared, which is, so if you think about R squared, it's 1 minus SSE divided by SST. I'm putting a P here to denote that the SSE depends on the number of variables. The SST, if you recall, it's just this. It doesn't change as you change the model, at least in your regression model. So this part is fixed. What can I do when I like include more variables? I make the SSE smaller, and the R squared goes up. What I can do is, or at least people propose, is just divide by the degrees of freedom, let's say. each one of the SSEs and SST divided by the degrees of freedom. This is called the adjusted R square. So this is like the a simple fix. And you can see it's like 1 minus. This is our estimate of the unbiased estimate of the variance in your S squared. And I'm writing it as S squared P because it depends on P. This you can think of as an unbiased estimate of the variance of Y, basically, which is not dependent on the covariance that you include in the model. So this adjusted R squared is going to be big, but like vary because of this piece. And this part is constant. And so if I do model selection based on R squared, it's equivalent to finding the model that has the smallest square, or the estimated noise variance, or you can call this MSE. So if you like, I guess Yonki, if you meant the low MSE, if you meant this MSE, then this is a good model selection criteria. That's the simplest model selection criteria. The reason why it passes as a model selection criteria is because there's this part that measures the fit, and there's this part that measures the complexity. So as I increase P, this SSE is going to go down. This one also goes down. You can see n minus P minus 1 goes down. So it's not obvious that squared goes up or down. Okay? So you're basically measuring basically the fit per the remaining degrees of freedom, or how much error you have per the degrees of freedom of the error. And the degrees of freedom of error goes down, and they balance each other out. So at some point, this might go down a little bit, but this goes down more. So this goes start to go up. And so this is the simplest way that you can sort of build the model selection criteria. Not necessarily the best, but traditionally reported. So you report usually R squared. It's easy to do adjusted R squared, and adjusted R squared is not necessarily going to be monotone like this, because of this fact. So adjusted R comparing models based on adjusted R squared is equivalent to comparing based on this MSE in this sense, or based on S squared, basically, your estimate of the variance of the noise. Okay, so this is the simplest model selection criteria. Does that sound good? You might ask why. I mean, is this a good one or not? That's not a question that I want to get into at this point. It's just a one criteria. How good of a criteria this is. It's a different question, which is really interesting and a little bit hard to answer. So what is the next one? So there are other measures, which is, so one thing is that you can come up with different ways of doing this balance. And in practice, people often do a couple of these things. And hopefully they have a consensus. These measures sort of point to a single model. And then you use that model, or you learn more about the theory and prefer more of one of them the other for various reasons. So the other measure is like AIC, which has some sort of AKKs, information criteria. That's the name of the guy. Information criteria, because it's derived based on ideas from information theory, which we don't go into. He proposed, based on some asymptotic arguments, that it's good. So this works for any model, not necessarily the regression model. So if you have a model, it has a log likelihood. If you recall, Anyone remembers what the log likelihood was? Yeah. Yeah, go ahead. Yeah, so let's say if you have a density parametric family of densities, usually the model is something like that. And then you fix your data, you view this as a function of theta, that's the likelihood. And think of this as it's not a probability, but if I multiply it by d of x, it's the probability to observe this particular value roughly um, under different values of under different models, basically. So the log of this, the log likelihood, let's call this L theta. So this is going to be log d theta of x. So x is so let's call this y because y here is the variable. All the variables that you get to see. So this is the log likelihood. So one natural estimator is the maximum likelihood estimator. We did this for the regression, and so in general you can compute the maximum likelihood estimator, and you can then form this AIC criteria. So there's this -2 times log theta hat, which in the context of regression, if you write this down, this is just the so the log likelihood is related to the sum of squares, if you remember. For the Gaussian case, in fact, you can do it here. So for the regression problem, you have two parameters, beta and sigma squared. And if you write things down, it would look like this. That's the likelihood. So the thing is, you can see this part sort of measures the goodness of fit of the beta. This part is constant, and this measures the goodness of fit of the estimate of sigma squared. So in general, the likelihood is a measure of how well you fit. So the higher the likelihood, the better you fit the data. So the higher the probability under that model. So you want to maximize the likelihood in a sense, which we already know. So the L at the maximum, how big of a likelihood you get is a measure of goodness of fit. So you put a negative sign here. 2 is like for the way that they drive this. So negative because we want to minimize this criteria. So you can, instead of maximizing the log likelihood, you could minimize the negative log likelihood. So they write it like this. So a model that has this part is small, like this, the smaller this part is for a model, the better the fit is. So you can see the negative of this, you turn these into positive. And so the smaller it is, the smaller the, this is the beta hat, sigma hat. This is the residual weight. The smaller this value is, the better, the smaller the residual sum of squares. Right. Okay, so this is a good measure of goodness of fit, and then the AIC adds a penalty, which is the number of parameters in the model. So times 2. So that sort of penalizes the complexity of the model. So when you try to minimize the AIC, you try to simultaneously minimize this and this. But usually when you try to make this small, you have to make the model more complex, so this goes up. You try to make it small, you make the model simpler, this goes up. So there is this trade-off. And then you can try to find a model that has the smallest AIC. So the model that has the smallest AIC is not necessarily the biggest model, because that would have a very big value here. Okay, there's another version which is called the BIC, which is more preferred. I'm gonna maybe talk about this. I don't have the slides here. Next time, that's from a Bayesian perspective, and you can show that actually is a consistent model selection criteria asymptotically. Don't have but basically, I'm not sure about the 2 here, but you would get a log n here, which is add the log n. So as your sample size grows, this part of the penalty also grows. N is the sample size. So that's the BIC. maybe I'll write it more carefully next time. Why there's a log n? Because it follows from the approximation, theoretical approximation, which we may or may not talk about. But this is often preferred. It's like a modification of AIC, which has good theoretical properties. In any case, it's not going to affect that much the smaller sample size. So it's not going to change that much. So if you do this in the context of regression, we know the MLE. So the MLE for beta is just our usual estimate, squares estimate. And our MLE for sigma squared, if you recall, is sigma hat squared, which is not exactly the unbiased estimate of the variance, if you recall, just SSE divided by n, rather than n minus p minus 1. But that's the MLE, it's fine. And then you plug this into the log likelihood. You do some simplification, and once the dust settles, the AIC, I encourage you to go through this. This is just some algebra. So beta hat is just the usual, it's the squares estimate. X transpose X inverse, X transpose Y. You don't really need to use the formula. It's just that this part is going to be, this is just going to be the residual square, which is basically what we call SSE. Okay, once you plug it in, you get the SSE, and this would be basically SSE divided by n. And you can see this simplifies here. So there's the SSE here, and this is SSE divided by n. So this is like n over 2. So this term basically goes away. This is just constant. And what you get is this only this part, which is 2. So AIC would be this plus a constant. So if you ignore the constants, because you're going to compare the models in terms of this criteria, the part that's constant doesn't matter. So this is not exactly AIC, but it's proportional, like not proportional, but up to constant. So there's a constant which we ignore here. So this you get -2 times this part, which is n log SSE divided by n, plus 2 times the number of parameters in the model, which usually is p plus 1. We have an intercept. There's a very nice criteria. You can see again that you balance the SSE and the complexity of the model. There's also n here. So it's a nonlinear criteria, but again, if this is this log is monotone increasing, the SSE goes down, this goes down, it's a better fit. The complexity goes up, this goes up, or complexity goes down, this is also better. There's a nice balance. Like in terms of the previous criteria, the MSE, it was similar to this. So again, there was an SSE component and a complexity part. This is a more elaborate version, but has the same feel. So balances the complexity of the model, the fit. Okay. I may talk about this more carefully next time, but you basically add a log n here. And it is a good improvement in large sample sizes. Okay, so these are 2 criteria. Any questions? Yes. Yeah. Yeah, they could. Yeah, this is not easy to answer. That's one of the things that people usually won't work with BIC, for example. BIC is like popular, but hopefully in the cases that you encounter, they point to the same model. If not, it's one of the questions that cannot be answered easily. I can't say which one you choose. If you see some theory, maybe you prefer one over the other. So this adjusted R squared, it just like, came up with it. It's not necessarily based on any sound theory. So these are derived from some theory, and there is some sort of, for BIC, for example, there is a proof that you can actually get the right model if your model actually is within this family of models, and the number of models doesn't grow, as it goes to infinity, then the model that maximizes the BIC with high probability is going to be the right model. So that's preferable. I may or may not talk about the proof. It's an interesting proof, but requires some knowledge of 100B advanced 100B. It's a good question. So hopefully you don't run into it soon enough. But they could have. It could have. So here's an example in your book. I don't want to go too much into the details here, but it's just, I think, the power plant, and there are a bunch of covariates. These are like called by their names. And you can see that they have done, this is all possible regression, all subset regression. So it's not all of them, but they did this. They're trying to predict the yield of the plant, and based on these covariates, and within each level, like I'm gonna have actually 10. So that's 10. 10 is the total number of covariates, and so they kept the four top competing models in each category. Category being the number of variables that you put into the model. And then you can see the R squared and the adjusted R squared. There is a CP Mallow CP, which I'm going to talk about next. There's the AIC and there's a S squared. So these four columns, you know what they are. And what they did is that, I forgot which criteria they used, but I guess all of them would point, like, give you the same four models, the four top models. So there are a lot of models, like 10. If you want to pick 5 out of 10, 10 choose 5 is a lot, but they pick top 5. In general, 2 to the 10 would be like there are 1,000 models, about 1,000 models, but definitely this is not an exhaustive list. So what you can see is just, and if you look at the R squared generally goes up. Okay, these models, that's like the model with everything. Like the R squared is better than everyone else. So highest. So that's what we expect. Adjusted R squared, however, you can see is not necessarily monotone. The one with n covariates has like R squared 0.79, but things that are here maybe are a little bit better. Not as much, but even something like this, you can see adjusted R squared is higher. It's simpler than, let's say, this model. Or like, this is comparable to maybe this guy, but then I'm going to go probably with this because as in any case, it's a little bit harder to judge. S squared, you can see, should have exactly the same conclusion as R squared. For example, if you look at this, this is the S squared, and if I compare with this guy, you can see S squared is slightly, actually the S squared are equal. R squared are, so there's some numerical issue because if the adjusted R squared are the same, then the S squared have to be the same. So I'm talking about is this line. So between these two models, for example, if you choose between these two models, you would go with, you can see the adjusted R squared is the same, but then I'm going to still go with the one that has fewer number of variables, most likely. Adjusted R squared alone can tell you, for example, that. But then you also have the AIC, and you can see the AIC is interesting. So it goes down, it's more sensitive, small here, and then starts to go up. So you can see the AIC here is bigger. Right around here, see again, this is like in each category, the best one, the best one. They're comparable, but then things go down. Again, if I want to, for example, choose between these two, and between these two, again, the difference, this is like subjective. The difference is not much, but I want to 5 here rather than 6. You can see it's like a little bit, iffy. But generally, these models are, it seems like the models that are working best. And, you can see the between this and this guy, there's one covariance. Either this or this seems to be. So you might want to go, for example, with this if you want. If this has the smallest AIC and it seems like the largest, just the R squared, sort of. So if you want to just perfectly do that, you could take this one. You go with this, it's also okay. But strictly speaking, you probably would take this based on all these criteria. So you put all of them together and then come to a conclusion. It's like practical data analysis. There's no easy answer, like not necessarily. If you do all these substitutions, then you can see, and you can see also the difficulty. So in terms of how close things are. So you're picking like between this and this, like there's 0.8 compared to, for example, this. There's a huge difference between this guy and this guy, but there's not much of a difference here. And you can also see there's not much of a difference here, but there's symptoms. So only the smallest model that gives you the smallest AIC or smallest MIC. Okay, does that sound good? Sort of. So this is traditional statistics. That's how it works. Okay, there's this idea. I'm going to talk about the CP, but sometimes there are these outliers that you talked about. And then if you change, like remove the outlier, then the whole business might change. So they had this case 26 deleted, and then you can see what happens to the AIC. For example, if I delete this case, sort of the AIC sort of drops more, and now this one that isn't, like the AIC was quite smaller than this a little bit. Now they have, this has a better AIC, for example. This is the AIC, for example. You see this squared also gets better. So this is the model that you might not originally go with. But remove one outlier, it suddenly looks a little bit better. So these are all like difficulties of doing model selection. And in the end, there is no clear answer. Hopefully, I mean, at least there is some sort of an overlap between the variables. These four are the same. Like actually, these four are the same. There is one variable that's different. One thing that would be very bothersome is that these two models would have very different subset of values. That's where you have to worry about, and that's where the debate about what is a good model comes into play. So in this case, fortunately, that didn't happen. So there's one variable. Say we're not very sure about this. They're both like N and PR explain the same. Maybe they have the same power. Then you can go and see whether they're like collinear or not. There's multiple linear. Maybe they can be like they're actually like exchangeable. But in this case, generally, sort of these things point to one of these two models. Let's say this was the one that has the best AIC before. This one, the one that has. Okay. Sounds good. Like difficulties of real data analysis. So what is this Mallow CP? Any questions? So Mallow CP. So this requires a little bit of analysis, and it's interesting. So I'll do this a little bit. So this requires us to assume that we have a true model. So suppose we have the true model y is equal to x beta plus epsilon. And for the true beta, some of the coefficients is 0. And let S star. So this is the design is n by q. So q is all the possible, like the number of, the potential number of values, all that there is. And then I have this as a star, which is actually the subset. So if you think about this, I can write all the models in terms of even the ones that don't have some of the covariates, I can write them as x beta, but I can set those coefficients equal to 0. So like if I have 3 variables and only the first one appears, I would have like beta 1 and then the 2 others are 0. So I have 3 columns here. If you recall, when this gets multiplied by that, this gets multiplied by this column, and these two get multiplied by these columns sort of get multiplied by these coefficients, and then I sum them up. So if I have something like this, column x1, x2, and x3, when I do this, I get beta 1 x1 plus 0 x2 plus 0 x3, which has the effect of only including beta 1. So I can write all the models like this, but some of the models have zeros, some of the coordinates of beta. So S star is the subset of the coordinates that are, let's say, active. So here's another example. Suppose Q is 5. So these are the columns. And then S star is 1, 2, 4. So I'm saying that the true model only includes variables 1, 2, and 4. So that's the true beta. So beta 3 and beta 5 are 0. And so you can see this reduces basically to the simpler model. If you recall that there's this is just the summation xj beta j, and some of the j's go away. So instead of doing it over q, I can say that this is equal to j in S star, basically xj beta j. I can only include the ones that for which beta j is non-zero, and I'm calling this matrix x sub star. It's common. This is the design matrix with only the columns that are in S included. So this is only include these columns and delete the columns that we don't have. So this is n by 3. This is n by 5. And then the beta, we also remove these. You can see the linear algebra, these are the same. So my model is going to be y equals x star beta S star, x sub S star beta S star plus. So S star is sometimes called the support of beta. So the support is the indices of non-zero elements. So this is the true support, or the true set of covariates in the model, which we don't know a priori. Okay, so the idea of model selection and regression you can think of as recovering this true support. Okay, you can think of it as a statistical problem of recovering a subset rather than a parameter. The model selection can be thought of as a subset recovery problem. And so one of the issues is that if you fit the model, the beta hat, all the coordinates often are non-zero. So you can't look at the zeros of beta hat to say those are the coordinates. So you can do the test and test whether they're 0 or not. That's one reasonable way of doing it. There are other procedures that actually estimate betas that are so-called sparse. They have a lot of zeros. And those are more modern approaches to doing model selection. Instead of trying to estimate the beta and then test whether they're 0, if you know that there are a lot of zeros, we can try to enforce that in estimation so that our estimate actually has a lot of zeros that shows the location function. I'll hopefully talk about that if you get a chance. But so far, this is the setup. Okay, it's a good setup to understand model selection. Is this clear? All right, now observe why I want to recover the subset. So let's see what is the idea. So pick some other subset S. So Q here is this notation is, I realized that I perhaps didn't mention. This is defined to be 1, 2, up to Q. It's a shorthand notation for the set of all integers 1 up to Q. pick a subset S with the cardinality. This is the number of elements in the set being equal to p plus 1. Okay, and let's say we fit the model. So the model would have, I can write the regression model that I fit like this. So I'm picking X sub S means I pick the design, the columns of the design that are in S. So for example, I had X1, X2, or X5. I might take S to be, there was some X0. So let's say this was 0. One of them is like, this is, you're assuming that there's an intercept. So let's say there's beta 0 here as well. Okay, yeah, this is fine. So this is the total number of, you can think of like, let's say X1 as the intercept, like the columns are all ones. In any case, this doesn't matter as much. So you understand the number of total number they include. So let's say S was 1 and 5, for example. Okay, and the size of S would be 2. That's 2 plus 2, and so X sub S would be this, the design of this column and that column. And the regression I'm going to fit is this. So I'm going to use this design and fit a regression. This would be like p plus 1 by 1. That's my regression model. You can see it's not necessarily the true model. But the true model, I don't know. I just assume that this is the model. I'm going to fit it. I get an estimate, which is alpha hat. And I get an estimate of the fitted value vector. This is an estimate of the mean of y. And so everything works out. It's just the usual regression. But I'm using subset S here as the index because if I do it for a different subset of covariates, I get a different mu hat. Okay, so all these models produce different estimates of the mean vector, different fitted value, and I'm indexing it like that. So a good measure of performance is how close this fitted value. This you can think of as the prediction sort of performance. So if you remember, this is giving you this vector is giving you mu hat as it's a little bit tricky to. I'm going to use X tilde. This is the ith row, the first row of the design. This is the last row of the design. And it's also, okay, this is not easy to do. It's just the first row of, it also depends on the S, but the first row, the second row, and so on. So basically, it's a prediction, like it's an estimate of the regression function for these cases. And if you look at this, this is the true mean value. So this is mu is x beta to true beta, which is x star beta star. This is the true mean vector, and this is your estimate of the mean vector. So this is a good prediction criteria in a sense. So if you take the expectation of mu minus mu hat, if this is small, it means that this is close to mu for almost all of them. And so this is a nice measure to measure how good a model is doing. And the expectation here is or the randomness in the noise that is in the model. So if you look at this, this gives you sort of a distance divided by sigma squared. So normalized by the noise basically. This gives you a nice measure of how well you're doing in terms of predicting the training basically data. One, it's a form of rescaled MSE for the parameter mu basically. Just mean squared error rescaled to have noise taken into account. So if you agree with this measure of performance, like a predictive, like measure for concentration prediction, you would like to find an S that minimizes this. So that's the idea of Mallow's CP. There are a couple of issues though. First, we don't know this sigma squared. And the sigma squared here is the noise variance. And the second one is that I might not be able to take this expectation. The reason why I can't take the expectation is that I actually don't know the true mu. true mu depends on the true beta star or beta star, which I don't have. So this is a good measure if I knew mu actually, and also sigma squared, but I don't know either. So Mr. Mallow's idea is to try to approximate this measure. If I try to approximate this measure, what can I do? This goes to the idea, it's good because it just reminds you of some of the things that we did. So if you look at this regression model, there's a hat matrix associated with the image of this. Okay, what was the hat matrix? What it is? The hat matrix is no, like the meaning of it. Prediction onto image of X. Yeah. So like one of the good things about it. What does it use for, or is it, how do you use it? Can I get this fitted value, for example, based on it? So, okay, so I'm going to call the hat matrix for this regression HS. So HS is the hat matrix. For this regression, it depends on which XS you use, okay, which subset you use. And so mu hat is going to be HS times Y. Okay, as I vary S, this H changes, mu hat S changes. And also the residual, I'm going to call it, let's say if you want, actually we don't need the residual. Okay, so, okay, if you want, the residual would be like I minus HS times Y. And this I'm going to write as HS perp. This is the notation that I'm going to use. It's just a projection onto the orthogonal complement of the image of XS. So if you do a little bit of calculation, you can show that this can be written in this fashion. Okay, why can it be written like this? Forget about this, maybe. You don't need this part. Mu hat is like that. So I want to say that this simplifies to that. So you plug in, you get Y minus HS times Y. Y is mu plus noise, if you recall. Mu is also X beta. Right? So what I get is that this is mu minus HS, mu minus HS epsilon. This is HS perp times mu. That's how I define it, or actually negative. No, that's true. That's this. And then the other term is minus HS epsilon. So when I square things, this guy turns out to be HS perp mu squared plus HS epsilon squared minus 2 inner product HS perp mu and HS epsilon. That's sort of the identity that we have. So if you square the sum of two vectors, that's what would happen. And then I need to take the expectation here. I put an expectation around everything. This part is deterministic. It comes out of the expectation. This part has a simple expectation. Calculate that expectation. So I get basically, might also get sigma squared. So what I have is the hat x is 1 over sigma squared times the first guy comes out, which is perp mu squared, plus expectation of this minus 2 expectation of this guy, perp mu, and then HS epsilon. Anyone knows what this last expectation is? Why? Good. Yeah. Okay. This is not transpose. This is perp. Right? This is not. This is a good question. Is this zero or not? This is not necessarily zero because mu is not. That's the whole point of this exercise because S is not necessarily equal to S star. So if S was S star, then mu would be in the image of S star, and then this would be zero. But in general, this is not because S is different than S star. That's the key point. This is the interesting part. So check. Then all not true. But you're right. So this is in the orthogonal image of XS, like the orthogonal complement of the image of XS. This is in the image of XS, and the inner product should be zero. These are orthogonal complements. So regardless, if you haven't done any mistakes, this would be zero, but this is also doubly zero because this expectation goes in. It's a linear thing, goes in and applied to this epsilon is zero. So it's very much zero. Okay. This term is zero. If you made one mistake, the other one would say that. So this term is zero, so you get these two terms. The only thing that you have to compute is this, and you should be able to compute this. This is based on the rank of HS. You should know how to do this, or you can actually figure out the distribution of this based on what we know. Epsilon is normal being zero and variance sigma squared I. And this is a projection. Projection matrix times epsilon. Basically, you get 1 over sigma squared HS per mu squared plus, I can move this inside, epsilon divided by sigma. There's the 1 over epsilon, which is in front of everything. I put it separately in front of this and in front of this and move it inside. Now this term, this guy is what is this guy? Normal, zero. Anyone knows what the distribution of this would be? HS epsilon squared. Yeah. Yeah, great. Rank of HS as the degrees of freedom. That's the result that we had. And the rank of this would be P plus 1, assuming that all these columns are like the full matrix, if it's full rank. Rank of this is the projection onto the image of XS. And they're just S, the number is P plus 1. We assume that they're P plus 1 columns, and we're assuming that they're sort of linear independent, so the rank is P plus 1. So this whole thing is going to be P plus 1 because the expectation of chi-squared random variable with P plus 1 degrees of freedom is just P plus 1. Expectation of chi-squared with R degrees of freedom is just R. So this turns out to be that P plus 1 here, and the other one is there. So that's the simplification that we got. This still didn't solve our problem because, again, you can see that both mu and sigma squared are unknown, but there is some simplification that we have. We have P plus 1. So it's interesting to note now that exactly because of this. So if the model is adequate, what we mean is that mu is actually belonging to the image of XS. So if I included enough variables that, so this means that S sort of, so S star is contained in this. So I picked the subset such that the true subset is in there. Then mu would be in the image of XS because I included the right columns. And mu is a linear combination of the columns of X sub S star. And those columns are in there as well. So mu would be in the image, and this would be 0. Because this part, as you pointed out, this would be 0. And then I get that this quant criteria is actually simplified to P plus 1. I guess for the subsets that are good, in the sense that they include the right variables at least, this criteria is going to be p plus 1. And then you can see that if I try to minimize this, I'm going to pick the subset that's small. So there are many of them that can contain true S star, but the one that has the smallest would be basically just this, it's a star itself. So when I try to minimize this criteria, you can see that I'm going to pick the right subset. So it has to be a subset that includes S star, but if it's bigger, this criteria would be bigger. So you can see it's a nice consistent criteria. So if I had this actually try to minimize it, this part, this is okay. So this is among the ones that for which S is S star is in S. If S star is not included in S, this would be even bigger than p plus 1. Anyone knows why? Otherwise, if this is not the case, the value would be bigger than p plus 1. Anyone knows? Yes. The first term is why is it positive? Why it is positive? The sigma squared is positive, but why this is positive? As a property, this guy is what? Yeah. It's positive semi-definite. You remember why it's positive semi-definite? There are different ways of proving it. Say about it. Yeah, so that's one way of proving things. Yeah, so if you look at H, because it's idempotent symmetric, if I look at X transpose X, I can write it as X transpose H transpose H X. So this is the same as H, and this is just H X squared, non-negative. Okay, that's one proof. There's another way. What is the other? Yes, eigenvalues of an projection matrix. What are they actually? Values. They're 1 or 0, so they're definitely bigger than or equal to 0. So that's another way of seeing that this guy is positive semi. It's positive semi-definite, so this has to be bigger than or equal to 0. Why am I saying that it's strictly bigger than 0? Because we are in this case. If it's 0, it's fine, but that would be this case. If it's not in the image, this has to be strictly positive. Because this is 0 if and only if mu is in the image. You can verify that. This quantity would be 0. You can see that if mu is an image, then this is 0. Argue the other way. If this is 0, then mu would be in the image. This might not be obvious, but from this criteria you can see. If this is 0, then h of x has to be 0. Okay, so means that this guy has to be 0. If this is true because of the idempotency, means use the idempotency and symmetry to prove that if this is true, then this is 0, but this is 0 means that mu is in there. Okay. In any case, it's either mu is in the image if this happens, or this is only happens if this is the case, or this is not the case. S star does not contained in this, then this would be strictly together. So you can see by trying to minimize this criteria, we first rule these cases out, and also among these for which is p plus 1, we're going to shrink it until we get this star. So it's an interesting consistent model selection principle. The issue is that we still don't know how to compute this. Okay, I still don't know. If I had this, then this argument shows that you would get the right model by trying to minimize this criteria. Is this sort of clear to people? Once you try to minimize the subsets that don't include, the S's that don't include all the variables, produce something which is strictly bigger than p plus 1, so you discard them. And the subsets that include all the right variables, they all produce this, but because I'm trying to minimize this, I'm gonna make t the smallest. The smallest possible one would be the subset, the smallest number of variables that contains this would be just so. So I end up being the right model. So it's a very good model selection criteria. It's sort of, in a sense, consistent, but we can compute it. We don't have a way to compute it. But is this sort of clear so far? Okay, so what Mr. Mallow proposed is to try to approximate this. And the approximation is that we built an unbiased estimator of it. We built something whose expectation is equal to this, and this is the criteria that Mr. Mallow sort of picked. And if you compute the expectation of this, this would give you the expectation of the SSEP. SSEP is basically the expectation of the residual sum of squares for this. That's what I mean. And this expectation is going to be equal to that. Why is that the case? Because SSEP is just the SSEF. You can say SSES if you want. So this is the SSE of the model with XS. This is the residual. So this is going to be I minus HS times Y, or that's HS per times Y, which is HS per times mu plus yeah. So this is the case. If you square it through the argument, this is similar to what we had here. So you square this, take the expectation. This was HS times epsilon. Now we have HS per times epsilon. So if you take the expectation, the first term is exactly the same. So you get this. The cost term goes away. The expectation of this squared would be just the rank of this, which is n minus p plus 1, or n minus p minus 1. Rather, it used to be like HS per. The previous calculation was something like that. The only thing is different is this guy. Now it's like HS per. And so I get n minus p minus 1 times sigma squared. I have to divide by sigma squared. So that's the case. And if you look at the expectation of this, then I divide by sigma squared, I get divided by sigma squared, divided by sigma squared. This goes away. And you can see when I remove this, so if you add this, you basically remove this and add p plus 1 here, which gives you, so this is like minus n minus and then plus p plus 1. So that's the thing. So when I add this term, I'm going to remove this and add p plus 1, which gives me this quantity. So the expectation of this criteria is exactly what we had before. And so this quantity is an unbiased estimate of the Mallow CP at the population level. So and then I can compute everything here except sigma squared. And at that point, you do like the ad hoc thing to plug in square. Up to this point is fine. This is unbiased. If you do this, no longer unbiased, but it's a good approximation because this squared is usually close to sigma squared. So that's the end of the day. This is the Mallow CP. So what we did is that we had a nice criteria that was consistent. We couldn't compute it. We provided an unbiased estimator of this. Hopefully it's close. Hopefully close to that. It's not exactly Mallow CP, but this still has like sigma squared in it. So this last calculation, do it for yourself, is exactly the same as before. The only thing that he did is to add this piece to compensate for the fact that now we get this thing, and this, you do this, we get back the value. So this criteria we can reconstruct an expectation, and then at the end of the day, you just ad hoc thing, place sigma squared to squared. In the end, this is a nice criteria. That's the criteria that Mallows came up with, and you can see again that there is this part, and there's also this part, which is a little bit. This is the this is not going to cancel out because this is the SSE based on the restricted model. this is the S squared that we get from the full model. So this is not going to be like this divided by n minus p plus 1 so that this cancels out. This is you're going to vary the models. This is going to change. This is your estimate for when you do the entire thing. And so this is going to go like down until you hit approximately p plus 1. When you hit approximately p plus 1, you're here, and your model is adequate. So you hope that you have included the right covariates. And then the idea is that to include variables in the model until this hits around p plus 1, and then you stop. So let me just do a very quick example, and then we're done. So in the power plant example, you have like, these are the number of parameters, and this is the Mallow CP. You can see for the number of parameters that are, so this is the line p plus 1. Okay, so with 4 variables, you're high, and then here with 5, you're sort of close, and then at 6, you start to hit this line. Okay, so this model, for example, is the first one that hits this. So the first time that you hit this line, then this is a good model. And you can see it's nice. It captures one sort of piece here, and that hopefully is the model that the other ones show. Okay, so that's the Mallow CP, and you can see also from this that the Mallow CP sort of this line is very large and starts to come down, and around 6 you hit like 6. That's the number of variables. Mallow CP is also equal to this. So this is the sweet spot, and it picks the good model. Okay, so I'm going to stop. There's a few points left, but hopefully next time we're going to come back and talk more about model selection and stuff like that. Okay, questions, comments? Sounds good. Thank you. See you next time.